Hello, good morning, everyone. Hello, good morning, everyone. Welcome to our Sunday class. Today, we're going to have the next 4 Sundays with Timothy Hamilton over here. Timothy Hamilton is a professor of physics at the Shawnee State University. And we actually made friends on Facebook. And it's so nice how social media can get to you to connect with people who have common interests. And that's what we realized with Tim. And I'm very happy that he's going to lead us through 4 different project topics over the next 4 Sundays. And it's going to be very exciting and interesting. And we'll be sharing with you a document which actually has the step-by-step process of what he'll be doing today. But you can try working with him while he's doing his thing. And just to mention, Timothy Hamilton essentially works on AGN. And he'd be happy to take your questions. So you can put your question in the chat window, and depending on the applicability of it, he can answer it at that time itself or towards the end, right? So welcome, Timothy. Thanks a lot, and we can start. Thank you.
All right. Well, thank you very much, Priya, and I appreciate again the invitation to do these presentations. Good morning, everybody, or if you're anywhere near where I am, good middle of the night. I'm going to be starting off this series of 4 talks with one on exoplanets. So the exoplanets are kind of our current term for the extrasolar planets, planets outside the solar system, are still, in my mind, a very recent thing. Now, by the way, I've got 2 screens, so if you see me looking over here, I'm getting something set up to show you. They were only found in 1992, I believe, was the first one. And so when I was already starting to study astronomy, and it went from having, we had known of 1 or 2 for a few years, 3 then, and then we had every year we might find another one, and there would be headlines every time you found a single planet around another star. And that continued for a while. The technique that was being used then to search for most of these planets was called the Doppler shift or radial velocity method. And the idea is straightforward enough. If you, let's see here, if you see the, make sure I am on, make sure I'm sharing my video. Okay, good. I'm holding my hands here. If you've got your star here and a small planet here, as the planet orbits the star, then the star is also orbiting the center of gravity between it and the planet. So while the planet makes a very large ellipse around the star makes a small ellipse around the center of gravity. But it's enough that because the star is very bright, we can see the motion of the star by looking at the Doppler shift as it goes around. The planet, in almost every case, is simply too faint compared to the star to make anything out from it. So its light is simply overwhelmed by that. So let's take a look at, let's take a look. What we did then was that got us 200, 300, 400, 500 planets found that way. And the problem is that finding them this way is very time consuming. You need to have a large telescope because you have to gather the light of that star, and you have to be able to get the spectral resolution. You've got to be able to make out some of these spectral absorption lines in the star's atmosphere to see whether it is shifting to the red or to the blue and back and forth like this. And you got to keep observing it day after day after day. So that was getting us hundreds of planets, which we thought was fantastic. But then in 2004, 2005, the Kepler Space Telescope launched. And it used a new technique, one that had only been pioneered a couple of years before successfully. And that was to look for the rare event when there would be an eclipse. If the star is here and its planet happens to be orbiting around this way so that we are in its orbital plane. And so that every time it goes around, we see a little blink right here from a partial eclipse. In that case, we would be able to see that with smaller telescopes, in fact, even amateur-sized telescopes. And that was found in the early 2000s. So after we'd already been doing this with the big telescopes for a decade, this proved that small telescopes can do it. In fact, a friend of mine who is an amateur astronomer has been able to do it in his backyard using nothing more than his camera and a telephoto lens, no telescope. And he's been able to get the kind of things that you're going to be doing this morning. So anyway, the Kepler Space Telescope ran for about 5 years in the first part of its mission, and it managed to find thousands of stars, thousands of exoplanets in that short space. They're still run, actually, they just ended. They continued the mission for a few years, but the gyroscopes had failed, and so they had less fine control of it, and they had to modify the mission. So anyway, we're going to be using the first 5 planets that the Kepler Space Telescope discovered. Now, Priya has put in the chat window a chapter of an observational astronomy book that I'm working on, and you can go ahead and download this chapter on the exoplanets. And I'm going to be going through this step by step in the order in which the chapter is laid out. So let me pull up my copy of the file over here. Okay. In fact, let me share my screen so that you see what I'm looking at. And share. Okay. Oh, that's our daughter's violin lessons information there. All right. So this is a chapter here. Let me just go over it very briefly with you. So in this, I go over the theory of it. And depending on where your background in physics lies, you may recognize some of this already. We'll go over measuring the size of a planet. We will create this exact transit here. We'll calculate the temperature of a planet based on that. And then we'll also take data from other observations on the radial velocity, which will get us the mass of the planet. And then we can calculate the density and try to figure out what type of planet it is, what its composition is. So let me explain that what this looks like. If you take a look on page 75, that's the 3rd page of the PDF file, you'll see that what we're plotting is the brightness. Let's get that there, make that wider. We're plotting the flux or the intensity of light of the star versus time, laid out horizontally there. I have it folded around, so we're looking at all of the transits, that's the crossings of the planet around the star, folded into one so that we get more signal to noise. And you'll see this very nice smooth looking plot here, and how you get this kind of a rounded bottom, and it comes back out, and then we see the star at full brightness. So we normalize it so that the average brightness of the star is simply 1. And then when the planet crosses in front of the star, it dims, and we can see the fraction of the normal starlight decreasing. In this case, it dims by about 1%. Now, if you think about the geometry, let's take a look over here. In fact, I'll go to where I've got a white page here. Okay, let me draw on this. I'll use this as a whiteboard. Now, annotate. Okay. So let's say that we have the star there, and then we'll take the planet and put that in let's put the planet in blue. All right. Now, if the planet, being much smaller than the star, is like that, and it's going to be moving, in this case, from the left to the right. Now, when the planet is not in front of the star, we see the full brightness of the star. But when the planet first makes contact, right here on the outer edge, that's called first contact. From that moment, the starlight begins to dim. By second contact, the planet is completely inside the boundaries of the star, in front of it, I mean. And so now we have gotten steeply down into that well. So let's take a look at the flux. It's full brightness here. We get, oops, up and down a little bit. That's simulating noise. All right, and then as the planet makes from first to second contact, you see it decreases like that as we get more and more of the planet covering the star. And by the time the planet is making second contact here, it's 1, that's 2, we're down at the bottom of the well. It also turns out, though, that stars tend to be brighter in the center and dimmer on the edge or the limb. That's called limb darkening, and the starlight is emitted a bit more straight outward. And so if the surface is turned away from us, it appears dimmer. So that means that at point 2 here, the planet is not covering a bright part of the star. If we get over here to the center, the planet is covering the brightest part of the star. And so we curve the bottom of this well down to that middle part there. And then it works its way back out. Okay, that's third contact. And then we get all the way out, and that's fourth contact. And there we go, and we're back to full brightness. So that is what a transit looks like in the idealized sense. All right, so now let's see here. I'll clear all of that off. Okay. So I'll move that out of the way here, and I'm going to bring up our archive. If I can find the right one. Here we go. All right, so what I want you to go to is take your web browser to archive.stsci.edu. Now, STSCI, that's the Space Telescope Science Institute, which runs the Hubble Space Telescope. And once we get it launched, it will also run the James Webb Space Telescope. They started up an online archive back decades ago, and it has grown to now where it hosts the data from many different space-based telescopes. And so this is called MAST, M-A-S-T, MAST here, which originally stood for the Multi-Mission Archive at Space Telescope, and they have now changed it, named it for their local senator, politician, to the Mikulski Archive for Space Telescopes. So we want to get the Kepler data. In order to do that, we will scroll down a bit here to what's called high-level science products, right there. This is exceptionally processed data, things that are in a final form that make it easy for someone else to use. Now, you can get raw data or more raw data, but we're going to start with the easy stuff here. So we're going to go to search the high-level science products, HLSP, and we're going to scroll down, scrolling. Oh, let's see here. List of all high-level science products. That's it. Click on that. Now, we're going to scroll down. These are in alphabetical order. We'll scroll down to K for Kepler. And you see that we have several different catalogs for Kepler. I will note that K2 is the Kepler extended mission, or mission 2, after they had the trouble with the guidance. And we're not going to be bothering with that. We're going to go to this one here, Kepler Objects, and it has an acronym of Kepler _ HLSP. So we can click on this to view it. Okay, this opens up in a new window. Now, These 5 planets here, let's take a look at that image. This was from the American Astronomical Society presentation that they had made the year after they launched, in fact. These 5 planets were discovered within a space of days of starting observations. It was incredible how quickly. So each of these planets is named Kepler and then the number. Now that is actually the name of its star that it orbits. Kepler 1, Kepler 2, Kepler 3, Kepler 4, Kepler 5, and so on like that, in order of discovery. So Kepler 4 is this star, and then we put a letter B for the first planet discovered around it. A, it by itself, would also refer to the star. So B for the first planet, C if there's a second planet discovered, D if there's a third, and so on. So Kepler's 4, 5, 6, 7, and 8. And to tell you the truth, I don't remember what the deal is with Kepler 1, 2, 3. Those three stars there. But anyway, these 5 were the first ones that they were able to work out. Now we're going to take the best one of these to start with, which is Kepler 6b. And that's because, as you see here, it has a very deep well in the transit. And that means it has a large planet as a fraction of the total light of the star. So let's go to that one there. We'll go back. Now we have 3 things in here, actually a little bit more. First, if you were to click on the target, let's go down to Kepler. Oh, Kepler 6b is the first one listed. Okay, right there. If we click on the target, we come to what the data look like as a quick look. This gives you an idea of what you're going to be dealing with. So they plotted it out automatically. Here we have the coordinates for the star. We have KIC, that means Kepler Index Catalog. Generally, we don't need to really deal with that, but it tells us the brightness of the star, in this case, in the red filter magnitude. And then the color, earliest and latest observation dates. Okay, so here we can make out 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13 different transits in this set of observations with a depth of about, well, 0.99, which means 1 minus 0.99, that's 0.01 is the fractional change, so about 1% of the light of the star is covered by the planet. Oh, let me go back here also. Notice that they plotted in the date, it's called Julian date. Now, Julian date is a way for people who do time varying observations in astronomy, and it is a date system. I think there may be a little bit of debate as to where the word Julian comes from, but I think it's generally agreed it refers to the Julian calendar. And it has a date of 0, which is sometime a few thousand years BC. It may be close to 6,000 years, 4 or 6,000 years BC. And so anytime after that, you could simply number the days, 1, 2, 3, 4, 5, and so on like that. It is, the numbers, of course, are by now are inconveniently large. You see 2, let's see, that's millions, 2,454,900,000 right there, plus these numbers here. So sometimes people will subtract a large number off the front of the Julian date when they publish a paper and simply write it down at the bottom like this, because you don't want to be carrying that number around. Okay, so let's go back to the page here. In order to get the data from the Kepler, we're simply going to click on the Kepler time series, and you can download it here. It is a text file. It is plain ASCII. Okay, I already have mine saved. And I'll show you that there is also what's called a ground-based time series, which is actually the Doppler shifting, the radial velocity data for the same star. We'll get to that later. But go ahead and download this file as well, and we'll load it up next. Okay, and down here they have some later targets, but we're not going to bother with it. Now, if you get out, and I'll apologize here, I have been, I've found that for my undergraduate students who are not physics majors, that it was easier to teach them with a regular spreadsheet that they use for other things already. I used to teach them with TopCat, but they didn't use it for anything else because we don't actually have physics majors anymore. And so I don't have people taking the upper level classes that would use it anymore. So when I was getting this out, because y'all have learned TopCat, um, I found that there is one function which is needed for this, which TopCat has, called the modulo function. However, my old copy of TopCat didn't have it. I went to go upgrade it and found out that I need to upgrade my entire computer because I can't get the new version of TopCat to run on it. So with my apologies, I'm going to be doing it on Excel as a spreadsheet, but I will tell you how to do it with TopCat to that point. And for the plotting and the calculations, the first part of the calculations, everything will work the same way. When we get to where we need to do something of a more just multiply these two numbers, but not for an entire table, at that point you can do it on pencil and paper, or you can write a Jupyter notebook, a Python notebook for that. And I'll apologize, I was going to try it in a notebook myself, but this would be the first time I've ever done that. So I'm going to try that for the next one. Okay, so we get out our workbook here. I'm going to open up. Let's see here. Yes, just open. And I'm going to go to where I have this saved. In fact, I think I have it saved here. All right, Kepler 6b. Now, yours just starts with HLSP and all of that, but I have managed, I have to import it because it's a text file. All right. Now, if you're opening it in TopCat, this is an ASCII file type, is what you want to tell it. It is not a comma separated value type. Comma separated value uses commas between the numbers of each row. The ASCII format will use spaces or tabs. Okay, now this comes up here. Kepler 6b. All right. Now, if you notice, there's DTR at the end of the file name. I'll get to that in just a moment here after I open this. So it is delimited, meaning there's a character, a symbol that's used to separate the columns. In this case, it's tabs and spaces. I'll treat consecutive delimiters as one. Okay, I'll start at the beginning there. Oh, and I'll put it right. Let's go down a couple of rows, a few rows. All right. Now, if you're opening that up fresh, I'll note that I have edited. I don't need that there. I have edited the file to get rid of what's called header information. So let me pull that up, what it will actually look like for you. Okay, here's one for a different target. And you'll see that at the very top, it has what's called header information. The hash sign, or what we normally call in the United States the pound sign, is used to mark a comment. Everything to the right of that is a comment. And so you can simply delete that there. But it does tell you what each thing is here. It gives comments about it. But here, column 1 is HJD, which means heliocentric. It's bound to the location of the sun, Julian date. And this next one here, this is the flux. In this case, they say detrended. Now, if you looked at that transit plot that I showed you from the pictures where they'd already done it, it was very nice and smooth. It stayed right at 1 until you get to the transit, that well in the middle. But in reality, we see these things when they come out of the telescope, they vary up over days and they vary down over a few days and smoothly most of the time. And that's variations in either the pointing of the telescope, the sensitivity, other maybe long-term variations with the variability of the star. I don't know what all goes into that, but they do that by they replace the flux for a given observation with the average flux of the 1 day before or after on that there. And that's detrending it, and it normalizes it. Oh, sorry, they take the flux and they divide it by the average for a day before and a day after, or 1 day wide window there. Okay, so we get rid of those, and I'm going to get rid of my reminders here. All right, so I'm going to abbreviate this first column as JD for Julian date, and the next one I'll label as flux. Okay, let's take a look at how this appears first. So in Excel, I'm going to scroll down. I'm going to highlight the entire set. In TopCat, you don't need to do this because you have only the 2 columns. So it knows that that's what you're going to plot. And you want to make a scatter plot. Okay, so for this, I have to go to Charts and mark Scatter. Okay, now one thing, and Dr. Hassan is right to get you to move away from spreadsheets for some of this stuff, because it's kind of designed for business use. It's not designed for scientific use, and it doesn't know much. It tries to make graphics look kind of fancy and so on, and it can take away from a good presentation of them. So here it makes the dots too big to see what's going on here. And I'm going to right click and format the data series so I can make the dots smaller. Marker style, automatic, it won't let me change the size. Okay, that's good there. All right, now we can see just what we saw in the preview image. All right, we have flux going vertically, and we have the Julian date going horizontally. Now, let's take a look at the first transit from this drop down here to the next one, which is this drop here. Okay, so let's see about how long that took. And I'm going to zoom in and I'll put the maximum time. Let's see here, 4, 9, oh, boy. I've got to cancel because again, it's not the smartest program for scientific plotting. So 4955 to 4950 to 4960. Let's try that. 24950. No, that's not right. 2524950. That's it. 2524950. Once again, I'm trying to find it here. Okay, let's see if I can do a better thing. I can copy that and format axis. Okay. And I'll put it 7 days later. Okay, there we go. Now we have a period, a complete period between the first transit and the second transit there. And that gives us a better look. So the next thing we want to do is to get, well, you see how few observations there are over the course of one transit. You see, the Kepler took 30-minute long exposures, and so each of those dots is 30 minutes apart, but the transits only take a few hours. So you have them very sparsely populated with observations there. So let's add something here. We're going to insert a column. Now, in TopCat, you're going to go and hit that green plus sign. If you pull up the column header information, and you create a new one, All right, now I'm going to call this one modulo Julian date, modulo JD. I recommend use the same terminology on yours. Now, in the function that we're going to use is the same in Excel and in TopCat. The only difference being I'm going to use capital letters and TopCat will use lowercase for it. So the modulo function means that you're going to we want to fold this over. We want to give the horizontal axis a maximum value, which is 1 period. And then the next observation past that period gets wrapped around to the beginning. So really what we're going to do is we're going to divide by the period. And then we throw away the dividend and we only take the remainder. And that's what we plot. So that's the modulo function. So we need to guess the period. Okay, and I'll put that over here. So what is the period roughly? Well, we could take it from, let's see, I'll take the last 3 digits before the decimal place, 957. That's 957, about 958. And that's 954. So I'm going to take out my calculator and subtract 957.7 minus 954.5, and I get 3.2. Now this is in days, and I'll just make a note of that to the right. By the way, we should go ahead and save our work. In TopCat, of course, you don't really need to do that until you're finished. But in Excel, it's a good idea to do it periodically. It will not save anything until you do it at the end, and until you tell it to. Okay, so I'm going to have this as Kepler 6b, and I'll just say example because I've done a couple of other versions of it lately. Okay, and if you're doing TopCat, you don't need to do that yet, just after you've got a final result. Okay, so this modulo function, in Excel, to open up a function, I put equals. In TopCat, you're going to go into the, I believe it's the expression window when you're adding the new function, adding the new column. And I'm going to write that it equals MOD for modulo. You're going to write lowercase mod. Now, what are we dividing by what? We're dividing the Julian date by, so we put the Julian date. If you titled it JD, then you put JD as a variable name, comma, and what you're dividing it by, in this case, the flux. I click on that, you will simply type out flux. Make sure, I'm not sure if TopCat requires the correct capitalization or not. Okay. Well, let's just see here for a moment. I'll show you how we can improve this in just a moment here. Now, in TopCat, once you've entered that, then it should go. In a spreadsheet, of course, you've got to drag it down. So I'm going to copy, and then I'm going to scroll down. There we go. Paste special. And I'm going to paste only the formulas. Okay. Now let me make sure. There may be, do you divide by the period? So, thank you, Priya. Sorry, I was doing that entirely wrongly. Yep, you're dividing by the period, which is why we have the period up there. Okay, so let me redo that here. So I click on that, and in a spreadsheet, you want to tell it that this is not going to be, you're not going to be copying down to whatever's below that cell over and over again. You want it to stay only in that one, so we put a $sign on those, so it's an absolute address. Thank you, Priya. I'm glad that you caught that. Yeah, that goes on. All right, so I'm going to copy, and once again, I'll drag it down and paste the formula. Okay, let's save that. So let's make a new plot, which is a phase plot here. We'll take the modulo Julian date and the flux. So in TopCat, all you have to do is select those two and make a new plot. There, all right. This is starting to look like something a little more professional, like how you'd study these. But look what's happening here. We've got uh, we should have a nice smooth curve coming down and coming back up. But look what we have here. We've got these interesting little cross patterns going on. What's happening is that we told it the period was precisely 3.2 days. And the observations are precisely every 30 minutes. And we're getting beats between these. We've got a different period for the observations, and we're doing a multiple of that as we go through. We have a timing between the observations, and we have a multiple of that for what we've assumed for the period, but it's not exactly right. So we need to adjust the period, and when we do, we're going to see a single curve down and back up. So let's try. At this point, what you really do is you guess. It's actually kind of fun. So let's try changing the last decimal place. Let's try going down or up and see if this plot improves. And you can tell when it will. So let's try 3.1. Oh, that's much worse. Okay, let's go back to 3.2. All right, what about 3.3? That's worse the other way. So it's between 3.2 and 3.3. So let's try 3.25. That's better. Maybe 3.27. Nope, that's worse. 3.25. 3.26, also worse. Okay, so we go down to 3.24. Aha, now we're getting close. But see how this keeps jumping around. And the reason is that we're starting on this Julian date here. But that might be in the middle of something. If we might prefer to start it. In fact, we should prefer to start it, say, a few hours before the transit begins. So here's the next thing we can do to modify it. So go back to your modulo Julian date, and we're going to say, I'm going to mark out here a starting Julian date. Okay. Now I'm going to copy this just as a first thing to try. Okay. Now, what we're going to do is find the Julian date of a time that is just about here. So it's 954.172. 0.172. Okay. Now that mine is rounded off there when you see it displayed, but that's okay. All right. So now what we do is we take our modulo function is the Julian date, JD, minus this starting Julian date. Now in TopCat, I don't know how to do any more sophisticated variables in it. I think you'd simply have to type in the number directly. So you're going to type in that number, whatever that is there. And I'm going to make that an absolute address. Okay. So now copy that and I paste it down. Again, you don't have to do that with TopCat. Paste special and formulas. Okay. Now see, this looks a lot better. And the great thing about this is we can adjust exactly where we want this folded light curve, it's called, to start. We could choose another point that's actually, we'd have to go back to the original to choose it because this has several different transits overlapping each other. Okay, I'm going to make the dots smaller, and in your TopCat plot, the default setting on the dots is probably pretty good, but you might you know that they have those density plots and things like that. We don't really want to do density plots for this because we're not looking at how plots cluster, how dots cluster. We simply want to make them small enough to see. And that's good. And I'm going to get rid of some of the borders on this and make it a nice red there. Okay, so now, and you know what? I can narrow it down a bit more. Let's say from I'll zoom in from about 1 to 1.6. There we go. And you can restrict the range of what you're plotting on the TopCat plot as well. So now again, you see we've got this beat pattern. We get the just that the interesting kinds of almost a moire pattern that you can get when you're plotting things at one spacing when it naturally occurs at a different spacing. Okay, so now we go here, let's see again, if we did 3.24, 3.245, that's worse. 3.243, better. 2, 1. All right, I'm just going to keep going down. Let's try 3, 8, 3, 6. All right, now we want to go into very fine changes. 3, 5, that's very close. 3, 4 is worse. 3, 4, 5. 3, 4, 6. 3, 4, 7. I'm going to go back to 6. That may be about the best we can get this here. Now, you're finding the period, in a way it's by trial and error, but you can know which way to go by how these points, whether they line up naturally or whether they don't. How do you assess what's better? Okay, so Dr. Hassan has asked about how do we know when we've got it? We expect to see an appearance like this. Now, all of them will look about like this here. So you don't have to know what your particular plot looks like. Um, it should look like it more or less like this in any one of the cases. Maybe it's very small and shallow. Maybe it's very broad like that, or maybe it's very deep, and maybe it's going to be noisy at the bottom. But the way that you check is by seeing that the entry and the exit lines here are as narrow as possible, where you could trace a smooth line between these here. And that's how you know when you've got it. In a sense, your brain is fitting a curve to this, and you're trying to minimize the differences between the dots and the curve. So you should have a smooth curve that's able to fit that there. When you get down to the very bottom, you're going to see a little bit of up and down noise on that, but you won't see as much as you're coming in and out because they're stacked on each other closer to vertical. And so that vertical displacement, the errors there, don't make as much difference. Okay, so I think that's about as good as we can get here. I'm going to narrow this a little bit more. Let's go from 1.2 to 1.42. Just see exactly, yeah, 4 is not enough. Let's try 4.2, 4.3. Okay. All right. And now we can start to do some science. So let's move that original flux plot down, and we're going to title this is a folded, let's give the planet name, Kepler 6b folded light curve. Now, a light curve is whenever you're looking at the change in brightness over time. And folded here is because we've used that modulo function to get all of the transits overlapping each other so that we get a very smoothly populated plot here. Now, in TopCAD, you automatically have the labels come up, but again, Excel is a little bit dumb and does not know how to do that unless you tell it. So let's do that here. I'm going to add, let's see here, this is the phase in days. And this is the normalized flux, normalized to the 100% being 1. Okay. All right, so what are we going to do next with it? Let me pull up an existing file that I've got as a guide. Okay, that's what we're going to work up towards here. I'll hold this off so that I'm looking at it, but you don't need to know it. You do not need to know it just yet. Okay, so what we can get next is if you take a look at the exoplanet guide that I have here. All right. The first thing we can do with it is to measure the distance from the star to the planet. So if you recall Kepler's third law, that the period p of the planet's orbit squared is proportional to the distance from the star to the planet, the semi-major axis, a cubed. We will assume for these simple cases that it's a circular orbit, and it doesn't really matter that much right here. Now, Isaac Newton had figured out that the constant of proportionality was related to the total mass of the star and the planet added together. In fact, that constant is 4 pi squared over the gravitational constant, capital G, times the total mass. So if we want to solve for the orbital radius, as I'm going to call it, the semi-major axis there, A, then we simply multiply both sides by p squared in this case, and there's a little bit of math involved here. We can make the assumption, now let me explain the notes. I tend to use this calligraphy looking, this very script style M for mass. And that's just because we also will be using capital M with the what we might call the Roman letter without any script to it to stand for the absolute magnitude of a star, a galaxy, or whatever. And because many papers have both mass and magnitude in them, this avoids some confusion. The subscript with the asterisk will represent the star, and a subscript with a P represents the planet. So this is the mass of the star plus the mass of the planet. Now, in all the cases that we deal with, the mass of the planet is much less than the mass of the star. Therefore, the sum of the two is pretty much equal to the mass of the star itself. Okay, so we can make that approximation and we'll simplify it a bit because, of course, we don't know the mass of the planet, not separately anyway. All right, so we put that in there for the total mass, and we solve for the semi-major axis A. We take the cube root of both sides, and we come up with this here. Now, this equation, 15.1, is the one that we're going to do. If you're doing it on TopCat, I'm not sure if you can just tell it to do a calculation like you would like a spreadsheet would. You might have to have a whole table. but you can do it very easily enough with a calculator. I'm going to put it into the spreadsheet, and I'll make these spreadsheets available so Dr. Son can post those for you afterwards, and you can practice with them. This way that you'll have a guide. Okay, but a cautionary note. We have to have the units working out. The mass of our star must be in kilograms. The period must be in seconds. That's a lot of seconds. And we'll come up with the semi-major axis, A, I can't highlight it there, being in meters. These are not the most convenient units to work with, but we'll simply have to convert them. All right, so let's put that in. I'm going to bring this off to the side so I can look at it while we program it here. And again, when you're doing this as a Python notebook, of course, it makes it very easy to program to calculate these kinds of numbers here. So, well, you know what? I don't have to retype everything because I already made myself a list of constants. Things that we will need. Things that I'll need anyway. There we go. So I've made this list of constants here. The mass of the sun is, roughly 2 times 10 to the 30th power kilograms. The radius of the sun in meters, Newton's gravitational constant, capital G, in newtons meter squared per kilogram squared. AU is the astronomical unit. It is the distance from the Earth to the sun. The radius of Jupiter, because we often will measure the sizes of extrasolar planets in Jupiter radii. The radius of the Earth, because some of them are smaller. The mass of Jupiter, the mass of the Earth, and for that matter, the length of the day in seconds. Okay. Now, right now, this is going to look a little bit messy, and the final form that I'm going to have posted will be nice and neat, but that took a lot of editing to make it everything be in the right place. So let's put, I'm going to copy these over here. Again, for those of you in TopCat, this doesn't make any difference at all. All right, so I want to have the period in seconds. So I simply multiply the period in days by the number of days, number of seconds in a day, and that's the period in seconds. All right. Now I'm going to highlight in blue the things that I enter myself, and our final results are going to be in red. Actually, anything the computer calculates will be in red, but I don't want to highlight that right now. Okay, so we need the gravitational constant. Let's see here. I'll just say the orbital radius, but it is properly the semi-major axis. And that is parentheses, equals parentheses, gravitational constant, G, times the mass of the star. Oh, we need to get the mass of the star. Well, here we get to go to another great resource, another archive, really, which is the Extrasolar Planets Encyclopedia. And I'm going to have all of these links posted as well, and I'll send them to Priya. So if you go to exoplanet.eu, now make sure you do not put an S at the end of this. I made the mistake and it goes somewhere else. But exoplanet.eu. And I'll put this into the chat window. That's a handy idea. Okay, there we go. So now I think you can just click on that. We're going to find the data that's known about the star. Now that's not cheating because the star has been observed by observatories for years and years and years. And so there's a wealth of data on these, and we need to know that data. We can't get it all from Kepler. So we go to all catalogs. Now we're going to search. Now, if you take a look here, this is a list of planets. They have 4,333 planets. And it's like, can you believe you live in an era when we know of thousands of planets? This still blows my mind because this was new as I was a student. Okay. So we need to search for the name. Now, the text that I have gotten you, that chapter, tells you how to search for the title. So in case you miss what I'm doing here, unfortunately I do the search at the end of the chapter. So we're going to scroll down to, it is the 8th page. Let's see here, obtaining stellar data, section 15.2.2. And it tells you the link there. You can even click on it from the PDF. And in page 8, which is listed as page 80 here, you see it says to go to all catalogs and then how to search for the name. Okay, so that's what I'm doing there. So you can keep that open off to the side. Now, they changed the syntax on me. It's a very picky syntax, and they don't have a lot of examples documented, although they do have a help function, but it took me a while of trial and error to get it right. So what we're going to do is we have to call it the name in this format. The capitalization does not matter. Capital or lowercase, either way does not matter. But we have to put Kepler-6 and then a space and then the letter B, and that must be enclosed in double quotes. And then we put N, capitalized, capital I, capital N, and then in lowercase name. Now, name is a property of the entries in the database. So for those of you who have done database queries like SQL and so on like that, you may be familiar with this already. So we're saying that this string here, in quotes, must be found in the name field. If you weren't sure exactly, you could simply type Kepler in name. And if we do that, I just hit return, and we get 2,334 planets in numerical or alphabetical order. Let's put the full form, Kepler-6 space B. I hit return, and we only come up with one. Now we've got the link here. Okay. Now this tells us information about the planet itself, but that's cheating. We don't want to do that yet. We just want to look at the star. We can look at that later to figure out how close we've gotten. We need to know its mass. This is its mass as a multiple of our sun's mass. And we're later on going to get its temperature and its radius. In fact, we might as well just do that, copy those in now. So the mass of the planet, mass of the star, is 1.209 solar masses. Okay, so let's put here star mass. I paste that number. I don't need it to be bold-faced. And this is in multiples of the mass of the sun. And that underscore means that everything to the right is a subscript. To tell you the truth, you can actually do that in Excel, but I'm not going to bother here. Let's convert that to kilograms. So we multiply the mass in solar masses by the mass of the sun in kilograms. All right, there we go. While we're at it, let's also copy in the star's radius and temperature. So there's the temperature. And that's in degrees Kelvin. We don't need to change it. And the radius. And the radius is in solar radii. So how many times the radius of the sun? And that we do need to convert. We'll put that in meters. So I've simply multiplied by the radius of the sun in meters. Okay. I'm going to make a note here that is star data below that. I'll merge those cells. There we go. Okay, that makes it a little bit easier to find things. Next, now we need to get the orbital radius. So if you look at the equation again, let's go back here. All right, this equation. Okay, so that's equal to, oh, my PDF viewer crashed. All right, that's equal to parentheses, gravitational constant, times the mass of the star in kilograms, times parentheses, the period in seconds, divided by parentheses 2 times pi. Now in TopCat you have the pi function, and I believe, Priya, I'm not sure if you might be able to confirm for me that it's simply written pi, and that works there. But again, actually you can't, this is not an operation on a whole table, so it is, okay, Priya confirms that yes, it is pi. So it's not an operation on a whole column of data, so you don't really need to do it in TopCat here. Okay, 2 times pi, we close those parentheses, we square that, we close those parentheses, and we raise this to the 1/3 power. Let's see if this worked. There was an error in my formula, of course. Okay, let's see if that was a matter of closing the parentheses there. Now probably, that's it. It needs to go here. Gm period over 2 pi quantity squared, close parentheses, hold on, I've got one more error. P period over 2 pi has to be squared, but that in Excel, pi has to have parentheses there. Okay, let's see if this looks reasonable. That's in meters, and we are going to convert that into astronomical units. So I divide by that. Okay, so we've got a number here, which is very, very tiny. 4.56 times 10 to the minus 2 EU. So that's 0.045 astronomical units. That's a tiny fraction of the AU. This thing, if we've even done this right, this thing is barely scraping the surface of the star. But that's actually true. It is scraping the surface of the star, or very, very close to it. This is what's called a hot Jupiter. Hot because it's very close to the star, so it's hot, and Jupiter because it's roughly Jupiter sized, as we're going to see. Okay, so that is correct. That's a success there. All right, the next thing we want to do is, let me see here. we want to get the size of the planet. So we've got the orbital radius purely from the period. Next, we can get the size of the planet by looking at how deep this well is here. All right, now this is also pretty neat because if it drops, if the flux drops by about 1%, let's round that up a little now, by 1%, that means geometrically, this is almost purely geometry, that the planet has a cross-sectional area, which is 1% the cross-sectional area of the star. If you take a look at the guide, it derives this for you and shows, again, purely from geometry, that you can calculate the radius of the planet based on that. I'll bring this over here. Okay, so I'll use F for flux. That means the intensity of light. Tot for total, trans for in the very bottom of the transit. And A is going to be the cross-sectional area of P means the planet and star means the star. So how much it dims, F total minus F transit, so that's 1 minus 0.99 roughly, that gets you 0.1, divided by the total, so we're getting a fractional drop, is equal to the size of the planet as a fraction of the size of the star in the cross-sectional area. All we have to do is to put the area in terms of radius, area is pi r squared, and then we solve for the radius of the planet. So the only tricky thing is to set this up. But if you think of it as a fractional drop is equal to the fractional coverage of the star, then you can set it up. And then it's just algebra to solve for this here. Okay, so our next equation, 15.2 on page 75, the third page of the PDF. Okay, so the radius of the planet is the radius of the star times the square root of 1 minus the flux in the transit to the total flux divided by the total flux. Okay, so let's take a look at the transit, the flux at the transit bottom. Let's say here, I'll call that F trans for transit. Now, how dim is it? We don't want to get the very lowest point because there is noise up and down here, but we're going to try to visually smooth that out and get where a smoothly fitting curve would be. And that's at about, that dot is pretty close to the average, 0.989522, 552. 0.989552. And I can't quite claim that much precision, but let's say 0.9896, 0.9896. Okay, and that's in flux units. I won't label that there. The top is F total, but that's just 1. That is true by the way we've normalized it, or the way they normalized it. So let's calculate the difference. I'll call it delta. Delta F, that's the difference in flux between 1 and the bottom there. So that's just equal to 1 minus this. Okay, very easy. Now, let's see here. Find my formula again. So we take the radius planet radius is equal to the radius of the star in meters. So that times. Now we take the square root of 1 minus the ratio of let's see, 1 minus F transit. We didn't even need to take delta F. Well, that tells you how much it drops. Okay, 1 minus F transit divided by F total, which is 1. So just that. Okay, and that's in meters there. Let's convert that to the radius of Jupiter. Abbreviate R Jupiter. So we simply multiply by the radius of Jupiter in meters. Well, that didn't work. That was this times the radius of Jupiter in meters. Oh, I should have divided. And I don't need scientific notation. There we go. 1.43 times the radius of Jupiter. So the reason this is called a hot Jupiter is because it's very close in. We'll get to the temperature in a moment. And it's very big. It's comparable in size to the size of Jupiter. All right. Now, I don't want to be going too long on this. I see we've got about 20 minutes left in the normal time here, and I'll try to keep it from going too far over. But I want to finish this first example, and then you can go through the others that we have. All right. Let's find the temperature. Now, to do that, we need to use what's called radiative balance. We'll go on to section 15.1.3 in the Exoplanets chapter. The idea of radiative balance is that we assume that the planet is absorbing, is giving off, is radiating as much energy per second as it absorbs from the star and from every other source of energy it's got. Because we assume that it's at a stable temperature. It's not significantly heating up or cooling off on average as it goes around the star. Over each cycle, it maintains a static case. So if that's true, then the luminosity, the power that's emitted, is equal to the luminosity or power which is absorbed by the star. So we've got black body radiation. The star emits light, which is absorbed by the planet. The planet heats up to some temperature, and it emits light as a black body, more or less, and radiates that back out into space. But we're converting from a small number of high energy photons, visible light, which is absorbing, and it's giving off a large number of low energy photons in infrared light. Okay, so we use the Stefan-Boltzmann law, sometimes called Stefan's law, which says that the flux emitted by an object, by a black body, is equal to sigma, that's the Stefan-Boltzmann constant, times the temperature of the black body to the fourth power. And that body here is the planet. Okay. Furthermore, luminosity is equal to flux times the surface area. And the surface area of a sphere is given by this. So that gives us the luminosity of the infrared light emitted by the planet in terms of its temperature and its radius. But we already know its radius. So to get the temperature, we just need to find the emitted luminosity, which is equal to the amount it absorbs. But absorption is different. That's given off by the star. And we get some fraction of the total light of the star hitting the planet. Well, how much of it hits the planet? It's a matter of the cross-sectional area of the planet as a fraction of the entire sphere surrounding the star at that distance. So if we imagine, let me try a little drawing here. If we have the planet, let's say, sorry, the star in yellow, I don't know if that comes out very well. It's over there on the left side of the page in the gray. And it emits light in a big sphere out here, like that. And that's all the light it emits over 1 second, and it travels out through space. But over here, I'm going to put the planet. a very large planet. This is not to scale. Okay, I'm trying to draw that, color it in there. Done poorly. But out of all of the light going out to there, only the light emitted in this tiny cone right here actually hits the planet. All the rest of the light misses it. So if we know the distance from the star to the planet, that's its orbital radius, which we've calculated, then we calculate the surface area of the big sphere at that distance, and we calculate the cross-sectional area of the planet based on its radius, which we've got too. All right, we divide the cross-sectional area of the planet by the surface area of this giant sphere here, and that's the fraction of the starlight which reaches the planet. Okay, I'm going to erase that. Okay, and I should put some diagrams in this chapter here. Okay, anyway, we work that out then. The luminosity of the star, what it emits, depends on its temperature and its radius. That's why we looked up its temperature and radius. And what is absorbed by the planet is simply the fraction of what I told you, but modified by alpha here. What's that? Well, there's something called albedo. Albedo tells you about the reflectivity, the brightness, essentially the shininess of an object. Albedo is 0 if you have something that's perfectly black, which absorbs all the light that hits it, a perfect black body. If it is perfectly white and shiny, it would have an albedo of 1, a reflecting surface. We're going to use the absorption coefficient, which is simply 1 minus the albedo. So we have to assume an albedo. And from looking in the planetary science books, an albedo of 0.07 is a reasonable guess for a lot of these, so we'll put that in. That may have been for a terrestrial type planet, but we'll run with it for here. So we modify it that way. Okay, and finally we solve for the equilibrium temperature, because it is an thermal equilibrium, we assume, and we get that. All right, so that's on page 78 of the guide. Okay, so the planet temperature is equal to the temperature of the star first, that's in Kelvin, we don't need to modify that at least, times parentheses again, 1 minus the albedo. Oh, I haven't entered the albedo yet. Let's put albedo, yeah. And we're going to assume 0.07. Okay, now, so it's equal to the star's temperature times parentheses, open parentheses again, 1 minus the albedo, close parentheses, times parentheses again, we take the radius of the star divided by the orbital radius, and we square the ratio. So radius of the star, let's see, where did I put that? In meters, divided by the orbital radius in meters, close parentheses, quantity squared, close parentheses again, make sure I've got the correct number of parentheses, 1, 2, 1, 2, 1, 0, okay. And take that to the 1/4 power. Hey, there we go. I mean, we can't justify that many decimal places. Okay, that's in degrees Kelvin. Let's put it in degrees Celsius. So that minus 273 degrees gets us Celsius. That is a very hot Jupiter. And that justifies the name. Let's do one more thing with this. We're going to find its composition. And this is actually, I think this is a really neat thing here, because you can get so far into it using only Kepler and observations of the star, but you can get really deep into it if you take the radial velocity data from another observatory. Okay, and now you're really going to be starting to do some planetary science. So we need one more set of data, and that's going to be that radial velocity data I had you save. So I need to open it up. Let's see here. I'm going to hit, in mine it's import. In Topcat, you'll simply just open it. Again, it's another text file, ASCII. It'll have header information. I've stripped mine out. And it ends in RVB for radial velocity something. Okay, this was Kepler 6b. Yes, don't want to get the wrong planet. Delimited, yes, again in Topcat it won't matter. Oh, but I want to start. Oh, that's okay, we'll go in there. Okay, and we'll put it there. Now, look at all of this stuff here. This is a much shorter file, but it's got much more header information. The only things we really care about on the header are the columns, the columns, and that's it. Now, see, we've got barycentric Julian date. So that is at the center, the center of mass of the solar system. Notice that this other one was the heliocentric Julian date, and there's not going to be a lot of difference for our purposes. We've got the radial velocity. Let's see, that's Julian date. That's radial velocity. Let me just put here JD, radial velocity in, what are the units? Meters per second. Okay. Positive is towards us, negative is away from us, I think. And then we've got other stuff on here, telescope and spectroscopy. That's the Keck Observatory in Hawaii and the high-res spectrograph. And we don't care about any of that. Okay, and I'll delete these as well. All right, let's put this up here. Okay. So now we've got the same issue that we had before. We have Julian date, but we need to wrap that around. So let's go ahead and do the modulo Julian date. So again, if you're doing it in Topcat, you've got a modulo function, MOD, lowercase, and we'll do it the same way as we did before. Okay, and so this is equal to, actually we can do it a little more, oh, yeah, we'll do it exactly the same way. We can even avoid the starting Julian date because we don't really care about it for this, but we might as well keep it the same. So we take the Julian date minus that starting Julian date, and I've got to do a little bit more with mine because it's a spreadsheet. And then we divide by, and as Priya helpfully reminded me, we're dividing by the period in days, not by the flux. I actually made that mistake twice today, once when I was preparing for this, and I corrected myself then. Okay, so again, for Topcat, this is a separate table. Now we're going to make a plot, a scatter plot of the modulo Julian date and the radial velocity. Okay, put that over here. I'm not going to go into the details on labeling this right now, but what you see here is a very choppy kind of a sine wave. If a planet is in a circular orbit around the star, then rather than in an elliptical orbit, then if you remember Kepler's second law, it's not going to speed up and slow down at different points there. And our radial velocity will be a perfect sine wave. On the other hand, if it's in a highly elliptical orbit, you can wind up with maybe long periods where it's down low at very uh, uh, radial velocities close to zero, moving very, when it's far away, it's not moving very fast. It stays close to zero, maybe a little negative, and then it spikes up suddenly as it swings around the star like a comet. And then that spike drops just as suddenly and it stays close to zero again. Again, that would be a comet-like orbit. Luckily, this doesn't have it, but we don't really care. What we want to get is the peak, the amplitude of the radial velocity, either positive or negative. Now, ideally, we would fit a sine wave to this, again, assuming it's in a circular orbit. But that takes a bit more work, and it's not going to change us that much here. That would be a good little project to work through there, though. So let's see here. The maximum here is 68.42. Let's see if there's anything more negative than that. Oh, yeah, negative 75.84. I think that's our winner. So we're going to put max velocity on here. We need that. I'll put V max, and I'll put an asterisk for the star. Let's move that over a little. Okay, let me read what that was again. Now, again, for those who are doing it in TopCat, you're just going to write this number down, negative 75.84. And that's in meters per second. Okay, now, why did we need that? Let's go back to our guide here. Let's see here, calculating temperature. We go forward. Stellar data, getting the planet's mass from radial velocity. So we take Newton's law of gravity and the idea that it's in a circular orbit, and we simply go back to your introductory physics course, and we take the equations for a body orbiting another in a circle. The mass of the, let's see, we've got the mass of the planet. Oh, here we go. So the mass of the star and the mass of the planet create a center of mass between the two of them. But we've got a problem that we might not be viewing the orbit from, in general, with the radial velocity method, we could be viewing a planet that's orbiting at some angle inclined to us. And the angle of inclination, we use the letter I. And so the Doppler shift only gives you only gives you the mass to within a factor of the sine of that inclination angle. Now, back when they were doing only Doppler shift, only radial velocity methods, back in the early part of the century, or well, in the 1990s, they had no way of knowing what that inclination angle was in almost every case. But when we have a transit, we know what the inclination angle is. We know that it's edge on. And so the inclination angle is 90 degrees. Okay, very, very close to 90 degrees, I say there. Now, we could actually, it could be a fraction of a degree off, but we don't really care about that for this purpose here. And so the sine of 90 degrees is 1, and so our equation simplifies. There it is, equation 15.4. So let's calculate that. Mass of the planet is the maximum stellar velocity towards or away, doesn't matter. We just need the positive value, absolute value. Semi-major axis of the orbit, A, times the mass of the star, and we divide it by the gravitational constant. All right, that's on page, what is that page? 81. Okay, so mass of the planet. Okay, we've got the mass of the star, we have the orbital radius, we've got G, we've got V max. We're ready to go. That's equal to maximum velocity of the star times the square root of, we don't need parentheses, just the first parentheses. Square root of parentheses, orbital radius in meters, times the mass of the star in kilograms divided by the gravitational constant g, close parentheses. All right, let's think of a drum roll here as we see what we get. What's the units? Oh, that's a negative. Huh. You know what I should have done? I should take the absolute value. Yeah, there we go. And that's in kilograms. Well, whoop-de-doo. I don't really run around with masses of planets in kilograms in my head. Let's put it in terms of the mass of Jupiter or the mass of the Earth. So that, let's see here, we'll have to divide by the mass of Jupiter in kilograms, 1.9 times 10 to the 27th. It's a little less massive than Jupiter. Let me get it out of scientific notation. 63% the mass of Jupiter. Let's see what it is in terms of the mass of Earth. 5.97 times 10 to the 24th kilograms. Number. It is 200 times the mass of Earth. That's a pretty good sized planet right there. Okay, so what we've got now is the mass of the planet. Again, we know now about why we were calling this a hot Jupiter. The surface temperature is 1800 degrees Celsius, and the size and mass, it is bigger than Jupiter, but it's less massive than Jupiter. Let's do one more thing here, and that's find the composition of the planet. Now, if we take a look on the next to last page of the Exoplanets chapter, I've gotten this from a paper, citations from that Gillon 2007 there, which they've done laboratory work and simulations, and they have calculated the compositions that you can expect from different, or the mass and radius you could expect for different compositions of planets, from pure iron, very, very dense kinds, to pure rock, which is actually less dense than iron, ice, less dense still, and the different mixtures of helium, of hydrogen to helium, 10% helium, 10% hydrogen, 50%, and pure. Sorry, that's 10% hydrogen and helium with a rocky core there, and then pure hydrogen and helium there. So it's not like pure hydrogen, it's a mixture of the two. Okay, now notice that they've overplotted our solar system. Venus and Earth are rocky planets with iron cores. All right, so we fall below the pure rock and well above pure iron. Uranus and Neptune are ice with a lot of gas, with a bit of gas. Saturn and Jupiter are between 50 and 100% pure gas. And then we have some of these stars here. This is the, what is it, the Harvard Draper catalog or Henry Draper catalog, HD there. Planets around some of those stars there. Now, all we care about are where these guidelines are. And we can plot it in Jupiter radii here and Jupiter masses up here, or Earth masses down there. Let's go with Jupiter masses and Jupiter radii. So I'm going to move that off to the side, and we'll simply calculate the density. Now, we want to put it, let's put it in kilograms per cubic meter. Let's see here. So we need to know the volume, wouldn't we? So that's going to be the total mass in kilograms. Let's see, where did we put, mass of the planet in kilograms, divided by The volume is 4/3 pi r cubed. Got to make sure I'm not messing things up. It's a little into the middle of the night here for me. So 4 divided by 3 times pi times the radius in meters cubed, planet radius, planet radius. Okay, and only the radius is cubed. Okay, let's put that, I don't want scientific notation. Okay, but you know what, let's convert that to grams per centimeter cubed. Now, grams per centimeter cubed, I've got to look up the conversion here. Okay, we're dividing by 1,000. So that's equal to that, divided by 1,000. Oh, that was easy enough to do. Let's give it 3 decimal places. Okay. Now, let's compare this to the density of water, which is 1 gram per cubic centimeter. So this has a density of less than 1/3 that of water. One of those senses where you see that thing about if you could put Saturn in your bathtub, it would float on it, ignoring all the compressing Saturn and that kind of issue. But anyway, it is less dense than water. And this makes sense because take a look here. It has a radius which is greater than Jupiter, but a mass which is much less than Jupiter. So it's a very fluffy kind of a planet there. Okay, now what composition do we get? Let's take a look at the mass in Jupiter masses and the radius in Jupiter radii. So 1.43 Jupiter radii and 0.63 Jupiter masses. Okay, 1.4 Jupiter radii. So that's here's the, oops, I'll just use my cursor. 1, 2, so about here. And then, oh, no, that was the wrong one. 0.63 Jupiter masses. So 1, 9, 8, 7, 6, 3 is right about here. And we go down to 1.4 Jupiter radii. So it's way up here. So it's somewhere in the top right-hand corner between these two red diamonds. It is a very low density planet, and we can assume then that it is probably a nearly pure gas planet. Now, there's another thing though. Now that I realize it, this is probably making an assumption. Yes, look here. Models for irradiated planets at 1/10 of an astronomical unit from a solar type star. Now, what's our distance? Let's convert that without scientific notation. We are less than 1/10 of a solar unit of an astronomical unit from the star. So we are half that distance away. And so the density could be thrown off by that there. But still, we know it's going to be a gas giant. And we've been able to get composition, a rough idea of composition, mass, temperature, density, radius, and period, all from a look at the Kepler data and ground-based radial velocity. So we've done the easy one here, but there are several others, which I will not be going over because we are out of time. What I would challenge you to do is to try Kepler 4b. I mean, really practice by trying all of these here, but take a look at Kepler 4b. That one has a very small planet compared to the size of its star. But it does make a noticeable transit. I'll show you the one I worked up earlier today in getting ready for this class. Let's see. That's not it. Okay, here we go. This is what I did for Kepler 4b. All right, so there's the flux, the entire time series, light curve. Here I narrowed it down to just the first period, and I was able to get the folded light curve like this. Now that doesn't look anywhere near as nice as what we got for Kepler 6b, but it's data. We can still make it out. What you want to do, you're going to have error on this. You'll never be able to get these to be very nice, smooth lines entering and exiting. Um, but you'll still be able to tell when you've got it the best you can. Then the other problem is that you're trying to get the minimum flux. You don't want to take the bottom dot because that's noise. You want to take it near the middle of where it bottoms out. So right about here, choose a point at that level or just read it off the side there. So 0.9993 is about as accurate as you can really get. Okay. And then I've got the radial velocity plot here, which you see is also very noisy. That is, well, largely because the planet is so small that its mass is not large enough to make a very strong change in the Doppler shift, to make a strong Doppler shift to that star. But nevertheless, you can do it. You'll have less precise results, but you'll be able to get something. And I'll tell you, you can do this yourself. If you have a decently dark backyard, a location, let me show you one other resource here. This is the Czech, as in Czechoslovakia, but now the Czech Republic, Astronomical Society. And they maintain a database, here we go, of exoplanet transits. And if you have a good quality camera, and that you can, and you have a telephoto lens, and you don't really need a strongly telephoto lens, 150, 200 millimeters would be enough for some of these. Maybe you want to go a little more, but let's say 200 millimeters or so. You can get some of the brighter stars that have large planets around them. And well, I'll let you search through this yourself. But I do have a friend who has managed to get this nearby our city, and he has been able to watch a transit that looks almost but not quite as good as Kepler 4b. Now, there are some questions here. Let me get to the chat questions. First of all, to Jinder Pal Singh, can we find the moon of a planet by this method? That is an excellent question. There has been talk about doing this, and I can't remember right now if that has been successful. So exoplanet. Oh yes, yes. In fact, moon transit. I can't spell. Okay, exomoon transits of extrasolar planets with moons. Yep. Okay. Oh no, that's the first one made of any planet at all. Exomoon indicators and high precision transit light curves. It looks like there is one. Most exoplanets found. Okay, so it looks like this is a guy's doctoral thesis here. Well, that's hundreds of pages, so I'm not going to try to read through that right now. But work is being done on it. The trouble is that those moons are usually going to be much smaller than the planets. If we're finding the best planets to find are Jupiter-sized planets, then you imagine that a moon around that planet is much, much smaller. So it will take more time, more transits in order to tease that out of the data. But in principle, it could be done. Another problem is, though, that the moon has an orbital period around the planet, which is not going to be an even multiple of the planet's orbit around the star. And so as the planet goes through its transit, the moon could be changing from one side of the planet to eclipsing the planet, which means that you get, that actually might be the best way, though, for the moon to sometimes be to the side of the planet and sometimes be directly in line with it where we wouldn't see it, and we could see the difference there. Well, anyway, there are, if you Google exomoon and transit, you'll come up with some cases on here. I was hoping for a graph, but I don't see one. Okay, I apologize for mispronouncing the name. I'll go with your last name, Sethi. In the case of Kepler 4b, the change in flux is so small, how good are the error bars on the flux? Well, we can get an estimate of those simply by looking at the folded light curve here. And so we could calculate the error bars on it by taking the standard deviation from the average here, from 1. So I'm going to make a very rough guess that the standard deviation is about out to here or so. What do we want to get? 2/3 of the points within that? So let's say out to about here. So you could do it. You could calculate it just by doing the statistics, and you isolate all the points which are not in the transit, and you take the distribution of those, a histogram of them, and you could calculate. Actually, a spreadsheet will have an ability to calculate averages and standard deviations. So yes, you could do it directly that way. Is it a trustworthy measurement? In this case, you would want to use propagation of error. And so all of the calculations that we have done, you can take, let's see here. The key point on this is going to be the flux at the very bottom of the transit, in the center of the transit. And what is the uncertainty? How big are the error bars on the flux there? So you estimate that from, you can estimate it from here, and it's going to be very similar down here because it's not getting that much dimmer. And then you can propagate that error through the rest of the equations. Just using, you take the partial derivatives for that there. Dr. Hassan says that TopCat can do some of that, so that is good. This is another reason I need to get back into using TopCat. Let's see here. Is it a trust, and what are the limits on such cases? That can actually get to be very complicated to ask what the limits are, because you have not only the flux at the bottom here, but also how closely have you modeled the period of the transit. And so I did it by eye, by looking at how well these dots coming in and going out lined up with each other very smoothly. But in the case of 4b, we have more uncertainty as to, let's see here again. Oh, that's my other example of 6b. 4b, exactly where the period is there. We can't get it as precisely as that. And so you'd have to, there are many different sources of error that you'd have to then propagate. And to tell you the truth, statistics was really my weak point in professional work. So I always make sure I ask the mathematicians about this stuff. Let's see, Vandana, if I'm pronouncing that correctly, what contribution does diffraction have towards the flux values, and can this be estimated? That is something I hadn't considered before, to tell you the truth, but I imagine it does play a role. There was a case in early solar system exploration in the 1970s where diffraction of, let me think here, I believe it was the planet Mars, played a role. What they were trying to measure the temperature of Mars, to measure its atmosphere by looking as it transited a distant star. So actually, when we talk about our own solar system, this is called an occultation, occultation, an occultation. But it's physically the same thing as a transit, except that this is not a planet going around the other star. This is Mars going around our sun, and then there's a distant star behind it. But this occultation method is used a lot for planetary studies and for other things in the solar system, like asteroids. So they were looking as Mars was going to cross occult this other star, and as because Mars has an atmosphere, as the as Mars starts to move in front of the star, then its light would dim. But the light of the distant star would dim, but it would dim gradually as it got through thicker and thicker parts of the atmosphere. And once it hit the physical surface of Mars, then it would shut off completely until the transit was finished. But what they found was at the very center of the transit of the occultation, and I'll say transit here, let's imagine it was Kepler 4b here. Okay, Mars starts to cover it up. It gets dimmer gradually in this case because the atmosphere of Mars. But at the center of the transit, there was a spike upward, and then it went down again, and then it came back out. And it is thought that, or there have been debates, but one of the explanations is that it was diffraction of that starlight around the planet Mars. Now, in the case of a hot Jupiter around that planet, the hot Jupiter would not have as sharp an edge. And so I think that would reduce the diffraction. But to tell you the truth, I don't know what role that might play. We do see diffraction when Venus, the planet Venus, transits our sun. I don't know if any of you were able to see the last transit of Venus in 2012. I'd observed it in 2004 and got good pictures, but in 2012 we had clouds. But Venus, if you take a look at it with very high precision telescopes, space-based telescopes and so on, you do see a diffraction around it where the sun is there. Okay, let's see other questions here. Tajinder Paul Singh says, thank you. I appreciate it. You're very welcome. I'm glad you enjoyed this. Ankur Chabra, if I'm pronouncing that right, says in the planetary mass radius diagram, let's bring that back up. I have closed it. Can you explain how are the pure iron, pure rocks, etc. lines determined? Oh, I guess I can do that without opening it. No, or at least I can tell you what they did in general, but they did simulations, and I'm not a planetary scientist, and so I simply don't know what those simulations included. But there's a lot of laboratory work that goes on with compressed states of matter and so on. You can put ices and things at high pressure and low temperature and so on like that, and see what their densities are. And so by doing that in the lab, they can build up a database of what those conditions are going to be like. And I think that that's how that was done. Let's see here. Sagram Barekar, again, apologize for mispronouncing. If any planet rotating very close around the star, is it close around the star? Does it make any difference in data or flux intensity during the transit? Let me see if I'm interpreting your question correctly. Do you mean the rotation of the planet on its own axis while it's orbiting the star? Is that what you mean? While I'm waiting for you to type that in, there is actually an interesting thing with the rotation of the star. Now, we cannot get the rotation of the planet from this, but let me pull up here, and I'll have to think of the name. Let's see here. The begins with an M. Let's see here. Exoplanet Transit. McLaurin. Let me see if that's the right word. No, hold on. Spectral change. I was wanting to say a McLaurin effect, but I'll have to skip out on what the name of it is. But anyway, as the planet transits the star, it will cover. Let's imagine. I'm going to go back to stop sharing my screen. You'll be able to look at me. All right. So let's imagine that we've got the star here, and it's rotating counterclockwise around its axis. And let's imagine the planet is also I'm going to get my hands this way, counterclockwise around its axis as it comes around. So they're rotating the same direction and the same direction as the orbit. So as the planet comes around here, okay, here's the planet. Let's see, I've got this drink here. So that's the planet. And this side of the star is rotating towards you. So this is blue shifted. And this side is rotating away from you. So it's red shifted. The planet going this way covers the blue side first, which makes the star redder. And then the planet covers the red side, which makes the star bluer. And so if you have a high precision spectrograph, you can see the spectral changes in the star, which will tell you which direction the star rotates. As whether the star rotates in the same direction the planet orbits, or if the planet's orbit is counter to the star's rotation. You just can't tell the planet itself. But that's actually really useful, and that's another great tool, because we could tell whether these solar systems are forming in what we might call a normal way. Like in our solar system, all of the major planets orbit the sun counterclockwise around the North Pole. And you only get occasionally some weird comet that'll go the other direction because it's from far out. Okay, let's see here. Rotating. How different is the MAST archive from other databases such as the NASA Exoplanets Archive and DACE? Now, I'm not familiar with DACE. The MAST archive has, and I'll share the screen again. Let's see, share screen. Yes, this one. Okay. Now let's go back to the World Wide Web. I just closed a tab of a paper I wanted to read soon. Oh well, I'll find it again. Now, most of what we do in the MAST archive is looking for things like Hubble telescope data. And so we can go there and we can search by targets. For example, the first quasar that I worked on, let's see, well, the second one anyway, PHL 909. I put the target in, and up come all of these observations of it. Let's see here, that was 2005. Let's take a quick look at it. And voila, there it is. Okay, and that's it there, that very bright one here. So bright that it's making a filter reflection on it right there. So most of what MAST is used for is things like this. But they also have something which, this being an archival astronomy class, would interest you. Oh, this is archives too, after all. There is what is called, and I would encourage you to play around with it, the Hubble Legacy Catalog, HLC, Hubble Legacy Catalog. Let's see if they keep moving these things around, so I'm not sure where it is right now. I'll have to find it. I can talk about that for the next time, I think. But anyway, that is another thing that is in the MAST archive there, and I would encourage you to try it there. So it's the something catalog. But anyway, what they've done is to imitate the Sloan Digital Sky Survey, where you have coordinates and you've got magnitudes. The only thing is that the Hubble observes in different filters from one observation to another, unlike the Sloan. Okay. Gitanch Aurora, again, hope I'm pronouncing it close. Isn't diffraction dependent on the comparative sizes of the objects? Yes, and also the distance between them and the distance to us. So that makes an effect there. Okay. I meant that if a planet is closer to the star. Oh, I see. Yeah, so you're meaning if its orbit is very close around the star there. Does that make a difference in the data or flux intensity during the transit? Yes, yes, to a small extent. And let me stop screen sharing and I'll go back to this. So imagine you've got a big star here, and let me get my planet. Okay, so now I've got these lights on back here because it's very dark outside. Um, Let me stand up a little bit there. That's better. Better. So my hand here is the star. Here's the planet. Now we are so far away from both the star and the planet that the planet will not look bigger or smaller if it's closer to us or farther from the planet, farther from the star, or closer to the star. It is so far away that we don't see any difference in the size of the angular size of the planet during that time. However, the distance from the planet to the star does make a difference in whether we will see it or not, and where does it transit. So if we take, I'll show you this way first here. If the angle between the orbital plane of the planet and us is 0, if the planet is orbiting, that will mean it will cross exactly the middle, like the equator of the star, as far as we can tell, all right around the middle there. Then it doesn't matter how close or far away it is. But none of them are going to be exactly like that, right? So let's imagine that it's off by 1 degree. Now, if it's close to its star, being off of that, having the orbital plane not aimed at us, but 1 degree above us, doesn't really make much difference. But look here, as it gets farther away from the star, if it gets up past here, we won't see the transit at all because it simply will not cross. It'll be too high for the transit. Now, they've estimated that somewhere between 1% and 0.1% of all the planets out there will be lined up well enough for us to see the transit. So we're missing 99% at minimum of all the planets when we look at the transit method. And when they when you look at the diagrams on the High Level Science Products webpage for Kepler, you see that they've got the star, they've got a dashed line, for this is when if the orbit were aimed exactly at us, and then they've got the planet some angle above or below that. Really, we don't know whether it's above or below, but we just know how far away it is from that center point. And if it transits the bottom edge of the star, right on the limb, you see the star is not as bright there on the limb. And so the planet will not make as much of a dip in the transit. But if it crosses through the middle, then it will cross the brightest part of the star right here in the middle. And so you're going to get a nice steep dip like that there. So it does make a difference to it. Okay. Let's see here. Can we use the same method to predict a black hole in a binary using, say, X-ray data? That is another good question. So they're working on, let me think here, black hole in a binary. You would not get a, your transit is more complicated with a black hole because you can't hide behind a black hole. The star would not be eclipsed by the black hole, but rather you would get a focusing of light, you get lensing of light by the black hole then. So you get an interesting gravitational lens, and that would change the brightness of the star, but not in the way we're seeing here. So instead of the brightness going down as the black hole transited in front, the brightness would go up. And that's because the black hole would focus that light. You'd have to have the alignment right, you'd have to have distances and so on right as well. But it would make at least some change in the brightness there. And yes, and they've looked for things like this. And I've seen proposals for where they of where people have been working on these kinds of projects there. Let's see here. John Mora, thank you very much. Glad you enjoyed that, John. After a while, when the data from the different surveys of the telescopes are made public, and they've already been passed through many computer programs and codes. Is it possible we'll still have a chance to make our discoveries in the public data? Yes. In fact, I did all of my research in graduate school for my PhD using the MAST archive. I didn't take any original observations of my own. All of mine were from the archive. And so people had already looked at them, but they were using them for something else. And so I was using it. I made, what was at the time, I collected what was then the largest collection of quasars over a certain distance from the Earth, um, measured at high resolution with the Hubble Space Telescope in order to see what their galaxies are like. And individually, some of the people had been looking exactly at that. Others were looking for something else. Maybe they were trying to measure the variation in the brightness of the quasars, for example. But I wanted to look at the galaxy. So if you're using it for a different purpose, already you have an advantage. Secondly, though, I was collecting a lot more than any one person had. And so by using statistical methods, by going for a larger set of data, you can use statistics in ways that someone who has only observed 3 or 4 or 10 maybe can't do. And that's been the advantage of these big archives. You may have heard of the Sloan Digital Sky Survey, which came out 15 years ago, maybe. And they have a 1.8 meter telescope, so it's smaller than the Hubble. It's on the ground and it has trouble with seeing, so you get a blurrier image than the Hubble can give you. But because they are mapping out the night sky with 5 filters, every so many minutes you switch filters to another set, and they get a large fraction of the sky observed in precisely the same way. Then they go through and automatically identify stars and galaxies and quasars. And so they follow up with spectrographs for certain interesting features. And so with that data, you have a massive amount of data observed in precisely the same way, which allows you to get large statistical sets. So when I was finishing my dissertation, I had 73 quasars observed at very high resolution, great views of the galaxies. A friend of mine was also looking at quasars with X-rays and with optical colors, visible light colors. And he used, for that part, the Sloan Digital Sky Survey. He had thousands of quasars, thousands of them, or of different kinds of active galaxies. I couldn't imagine having that many objects there. So while each individual observation was not as good, because he had so many of them, he could start to do things that I simply could not. So yes, that's a reason for these archives, is because we expect that people will be able to do much more work with them than just what they were originally proposed for. Okay, well, if there are any other questions then, appreciate everybody listening in. I've really had a good time with you tonight, or this morning.
Yeah. Yeah, so I'd first of all like to thank Tim for an excellent session. That was a really nice session. You gradually walked through it. And I would like to add to what you were saying, that the best part about archival data, I think, is the quality of the data. Like you said, the amount of data as well as the quality of the data. So it's not and hence there is so much of the potential of it. And like you mentioned, even we have students working at present, PhD students are all working only on archival data, because
Yes.
for the student to get actual data is good for experience, but it works out so much better with archival, because you know how much you have, and once you know how to handle a certain kind of data, there is no end to the amount you can get, right? You have access.
And it's so exciting to me that we are living now in a time when these big databases are online.
That's
I mean,
right.
think about 40 years ago, we didn't have this. You would have to travel to one of these places to get it. 30 years ago, we were just starting to get what Hubble had it, and I don't know if anybody else did at that point. But with the internet and with the images being digital from the beginning, this has opened up a massive, a completely new approach to doing astronomy.
Yeah, yeah. So I would once again support that's the whole purpose of this course, because this is not just meant as a hobby project. These are all going to be serious science projects, at the level of a PhD or scientific publication.
Mm-hmm.
Yeah.
And also virtual observatory tools. There are all these efficient tools available for them to analyze, visualize, and deal with the data. So that's the whole idea. Yeah.
Yes. So I would say democracy at its ultimate best, where
Yes,
Yeah, let's see.
yes.
access is there to everyone without any this thing, right? So I'd like to thank Tim again for that excellent session. And with
You're
Tim's
welcome.
permission, I would give people the homework that would be uh, doing the Kepler 6b work with TopCat. And I would say that with TopCat itself, they can get a better handle on the error bars. So it would mean estimating the parameters which you did estimate, but with error bars using the methods you were saying, using the standard deviations, etc., which can be done reasonably easily with TopCat. Or you are open to use whatever method you want. You can use Jupyter notebooks or whatever method suits you best to find out the error bars for the values that Tim found out. And obviously, there is the also work with Kepler 4b, which has its own constraints and its own peculiarities. And so I would encourage students to also work on 4b data to actually check how do you manage with things like that. And that would be a good learning experience. Yeah. So thanks again, Tim, and we'll see you next Sunday
You're
once
welcome,
again.
Priya.
Yeah.
All right,
And
I'm
do
looking
let
forward to
me,
next week.
yeah. And do let me know if the students need to install some software for next Sunday. Or
Okay, certainly.
yeah, so they can do that. Yeah.
Hmm.
Thanks a lot. Thank you,
You're welcome.
everyone. Yeah. See you.
Goodbye, everybody.
Bye. Bye. Oh, no, no, it's not yet ended. Just end.